Right, this is the pivotal part of this topic. What happens in the next 10 minutes is going to basically be the foundation of your understanding of the principles here. We're talking about PV diagrams, graphs of P against V in the following 4 thermodynamic processes. Isobaric means a constant pressure. Isochoric or isovolumetric means constant volume. Isothermal means that the temperature stays a constant, which means that it's going to be a fairly slow process. Adiabatic means that it happens so quickly that there is no time for the thermal energy to go into or out of the system. We have to draw and annotate thermodynamic processes and cycles on PV diagrams. Pressure against volume. Here we have an ideal gas. We're going to look first at the axes. Pressure is the vertical axis, volume is the horizontal axis. What happens when we change the volume or change the pressure or both? What we're going to look at first is isobaric, constant pressure, which means that the pressure stays the same. So we're going to be looking at horizontal lines, which means the volume will be changing. The pressure will be the same. We need these 2 equations. These are 2 key equations to figure out what's going to happen to the other quantity. Isobaric expansion, which means at a constant pressure and is expanding. I'll give you what we have here. Okay, W is going to be positive, which means the volume is expanding. This gets bigger, the volume gets bigger, the pressure is staying the same. If the volume is increasing, the temperature must increase also. So we know that this is going to be positive as it expands. We know the temperature is going to increase, so this is going to be positive as well. That's going to be a positive value, which means that also Q must be a positive value. So these have 3 positive values. What about an isobaric compression? This is going to be a negative value. If the volume goes down with a constant pressure, the temperature must go down. So this is going to be negative, that's going to be negative, so this must be negative. Now we're going to look at isochoric or isovolumetric changes. Let's take the first one, the one on the left. We know that the volume is staying the same. The pressure is increasing, which means that the temperature must increase. This work is going to be this 0 because there's no change in volume. Only when it expands or contracts is the work done. But we know that the temperature is going to go up when the pressure goes up, and therefore the heat must flow in. So that, in other words, there must be Q is a positive value. And that makes sense. When you heat a fixed bottle of gas, let's say, the temperature will go up and it doesn't expand. That makes sense. On the other hand, if it's a reduction in pressure, this will be negative, and you can do the same thing here. W is 0, delta U is the temperature is going down, and therefore the thermal energy input is energy is coming out, so it's going to be negative. It's like taking a glass bottle and putting it in the fridge. It loses thermal energy to the fridge, and the temperature inside will go down, and the pressure will go down. Adiabatic. This is a fast process where there's no chance for heat to flow, and it's a very steep process on the pressure volume graph. So adiabatic expansion means there's no flow of thermal energy. So Q is going to be 0 because there's no flow of transfer of thermal energy. Here we have the volume is expanding, which means work is going to be positive. If this is positive and that's 0, delta U must be negative, which means that if a gas expands rapidly, the temperature must go down because delta U is going to be negative. So there you have it. Yeah, the internal energy drops. An example of this would be probably what you've seen already, which is making carbon dioxide. We get a large value for W. There's a rapid expansion of the gas. The Q is 0 because it happens quickly, which means the temperature drops. Another example is the cold side of a fridge. There are cylinders which make a fluid and a gas expand very rapidly. So they make the inside of the fridge cold because it's the gas is expanded when it goes into the tubes into the back of the fridge. The universe is also an adiabatic process like this. There is no energy flowing out of the universe, but it's expanding, and yeah. But this is a little bit of a dodgy one, so perhaps we'll leave that one. An adiabatic process, which is a contraction. Volume is getting less. If the volume is getting less, W must be negative. This is going to be 0, so delta U must be positive. So in other words, you get a volume of gas and you squash it, the temperature will increase. An adiabatic compression, in other words. Yeah, so the temperature rises. An example of that is when you squash a volume of gas of some kind, like a bike pump. A diesel engine works on the idea that when you have the diesel in the cylinder, it's squashed so quickly that there will be a rapid change in temperature. The temperature will be so high that the diesel will ignite. There is no need for a spark plug to ignite the fuel. And the hot side of a fridge. Here we have a compression on the behind the fridge. So when the fluid goes onto the back, outside the back of the fridge, there's compression. So that heat is basically concentrated outside the back of the fridge, and then it's able to flow away from the back of the fridge. Now we're looking at isothermal processes. This is where there's no change in temperature. Here we have an expansion, so there is work done. The internal energy is constant. It has to be because there's no change in temperature. So if this is 0 and this is positive, this must also be positive. So it basically means that if you heat up a container slowly, it will expand, and it will do work against the surroundings. So heat can be turned into work. We have what's called a heat engine. Heat turns into work. So yes, you can look at that. This is the opposite when we have isothermal compression. Delta T is still 0. Work is done on the gas, so W is negative, which means that that the thermal energy must also be negative as well. And it means that by squashing a gas, you can get it to give out heat. The body of gas loses heat to the surroundings. So by doing work, you can produce heat, which is given out by the gas. This is called a heat pump. What's going on here? Here we have an isobaric expansion. Remember that the heat flows in, then the temperature increases. You want to try looking at this again, you can prove to yourself that happens. The pressure stays the same, the volume increases, the temperature must increase. Positive, positive, this must be positive as well. And so on. So you can look at these. Take the time to stop and figure out what is happening to the thermal energy, the internal energy, and the work. Here we have one process followed by another. It's isochoric heating followed by isobaric expansion. Now we have two processes here. Which one is isothermal? And it's not easy to see the difference. One is adiabatic, one is isothermal. I can tell you that the one that has the steepest part of the curve is going to be the adiabatic one. The one that has the y is equal to 1 over x relationship is going to be the isothermal curve. In which process would the temperature drop? The isothermal is where the temperature does not drop. So it has to be the adiabatic one, which is a steeper curve. Here again, use the first law of thermodynamics to figure this out, and the gas equation. Here's another process. Which one is adiabatic? Well, the one that has the steepest one is the adiabatic. The B is the steepest, and there will be a temperature increase in B because there's no heat flow. It's adiabatic, happens quickly. There again, use the first law of thermodynamics and the ideal gas equation to figure this out. I'm going to pause there.